Hello, Algebra 1 students. We are going to be running through lesson 6.3 today, which is on reducing square roots. Now, there are a bunch of important concepts in this lesson, but the very first concept I want to talk about, even before we do the opener, is what is a square root? You should have seen square roots in 8th grade or maybe 7th grade, depending on when you're watching this video, but we've found that many students forget what square roots are, and it takes a couple examples to jog your memory. So I'm just going to use the top of your paper, and please do the same thing here, and let's see if we can remember that. So the first one I'm going to ask you about is the square root of 36. You also might notice, by the way, that I put a little tail on my square root here. And you'll see square roots over here. Most computers don't put a square or put a tail at the end, and I think most teachers don't either. But I had a professor that did that in college, and I liked it, so I put a little tail. You don't have to. But why don't you guys go ahead and think about the answer to the square root of 36. And hopefully you know that the answer to the square root of 36 is 6, but if you didn't and this is new, that's totally okay. There's our answer. Now you might be looking at that thinking, why would the answer be 6? How does 6 relate to 36? And so it might help us to try one more really quickly, and we look for the square root of 25. And you might start to connect here and say, well, if the square root of 36 is 6, I bet the square root of 25 is 5. And you'd be right, the square root of 25 is 5. Do we know why yet? Well, I'll spoil it for you and we'll focus on that 5. The square root of 25 is 5 because, I'm going to abbreviate because 5 times 5 equals 25. Square roots always look for a number times itself, or two of the same number that multiply to equal the number inside the square root. Now, that's all fine and fun, but do all numbers have square roots? So let's maybe look at two more of these. And actually, let's work backwards. So could you remind me about what 8 times 8 is? Well, 8 times 8 is, I think, 64, which means we know the square root of 64 is 8. That's cool. And then also, let's do 9 times 9. It seems like I'm pulling these numbers out of nowhere, but it is important. 9 times 9... well, that's 81. Hopefully we know that. You could have used a calculator. We are going to be using a calculator a lot today, so you may have to pause the video and go snag that calculator. And why is that important? Well, that helps us know that the square root of 81 is 9. Okay, now that we know that, go ahead and pull out that calculator. And let's go ahead and find, and I'm going to highlight this in purple up here, the square root of 72. And it's a little bit trickier to find the square root of 72 without a calculator. In actuality, it's a lot trickier. Because if 8 times 8 is 64, if 8 times 8 is 64, we know the square root is 64. If 9 times 9 is 81, then we know the square root of 81. 72 is somewhere in between 64 and 81, which means the answer has to be somewhere in between 8 and 9. But is it 8.1, 8.2, 8.5? And that's where our calculator comes in handy. Now, I imagine many of you, when I said calculator, took out your cell phones, which is great. A cell phone always has some sort of calculator built into it. But spoilers, usually the calculator built into your cell phone isn't nearly as good as other free calculator apps that you can download. I'm going to suggest that you download the Desmos scientific calculator. There's actually 2 Desmos apps. There's a graphing calculator and a scientific calculator. I'm going to suggest the scientific calculator so your keyboard looks like mine, and that way we're all working the same way. And then to do a square root on here, it's pretty easy. Just type in the square root, and then we just go with 70, and my keyboard does not like it when I don't use the mouse, but 72. And then your answers show up on the other side. Square root of 72, 8.485. Oh my gosh, that's a lot of decimals. Now, if you're like, no, I refuse to download another calculator, or you're like, no, my photos from Snapchat are taking up way too much space or something like that, I can't even fit this tiny little calculator app on here, that's okay. your phone will still work. So two things to note. I used just my iPhone to get this image, but if you search Desmos on the App Store, you're going to see two apps come up. The first one is the Graphing Calculator app, and that one's awesome. We've used it before. We'll probably use it again. You should have it on your phone. And the Graphing Calculator app, even if you zoom in here, has a square root button, and so you could just use this if you'd like. However, directly underneath that on the App Store, there's the Desmos Scientific Calculator. Look, it even has a square root symbol right here, doesn't it? And so you can go ahead and grab that if you want to just have the calculator portion. Now, I mentioned that your calculator will work fine for square roots, so I took a screenshot of an older iPhone operating system, but it still works, and we have the square root button circled over there. So if you wanted to find the square root of 72, you'd type in 7, then 2 first, so you'd see 72 up here, and then you'd press this button. It looks like a little 2 and then square root of x, and that will all get you this same answer of 8.485 something something something. Hopefully you remember in this class, in Algebra 1 and every class forward, we're always going to try to go out to 3 decimal places. This decimal actually goes on forever and ever. It's infinitely long. So I'm going to use that squiggly equals sign because we're not going to write the whole decimal. Writing an infinite number of numbers is probably a waste of time. And then we're just going to write the first 3 digits past the decimal, 0.845. And I always like to put those 3 dots at the end to show that it continues going on. All right, now that we have that and you know how to use your calculator to find square roots, please go ahead and let's try the opener. Your goal is to decide which of the reduced forms are equivalent to the original expression. Now, it says reduced forms. Not all of the forms are reduced. For example, this original expression is 5/10. 1836 is equivalent to 5/10. So you would definitely box this one. But there are others as well that are also equivalent to 5/10. So work through, pause my video at this point, try these 3 problems, and then we'll come back together and see how you did. Ready, set, go. All right, and you're back. Well, looking through these, there's a few ways to do this. We've learned reducing and maybe scaling up, scaling down fractions, simplifying fractions before. In fact, you first start to learn this in about 4th grade. And so we should realize that 18 over 36 is the same as 5/10, because if you double the numerator, you get the denominator, right? The same way, we should also realize that 1/2 is the same. Something that all 3 of these have in common, 5/10, 1836, and 1/2, is if you put them into your calculator, and I'm going to again use the Desmos one over here, and we're going to delete all this. Move that out of the way. If I do, and remember to do fractions on Desmos, fractions are a fancy way to write division. If I do 1 divided by 2, we're going to get the fraction 0.5. And in fact, this button over here will even turn your answer into a fraction. If I were to do, and let's clear this out, if I were to do 18 divided by 36, we would get that same decimal again. And so hopefully we'd start to realize that if we turn A and the original problem and D into decimals, they are all the same decimal. They are all the decimal 0.5. B and C do not match. These are the numbers 2 if you put them in top divided by bottom. Problem 2 is very, very similar. Problem 2 says which one matches 7/4. So you could put this into your calculator right away and see that this is 1.75, so it clearly matches C. You might also remember that 1 3/4 is 1.75. 7.25 is too large, and 12 into 21. Oof, can we reduce that? Can we divide by 3, I think? And this gives us 7/4, which is correct as well. Those all have the same decimal value, they're just written in different ways. And so that brings us to number 3. This is our new topic for today, reducing square roots. Because what ends up happening is if you write any of these into your calculator, any of them at all, let's try 3 square roots of 8. Let's do this over here. So we have 3, oops, we should probably clear all this out first, huh? So we have 3, and then we type in the square root of 8. Does that decimal look familiar? 8.485? It should, because it matches the same decimal as the original problem. And any problems which have the same decimal as another type of that number are the same number, just written in a different form. And in fact, what I think you'll end up finding here is that all four of these have the same decimal as the original problem. So all four of those are a different way to write the square root of 72, which should bring up two questions for you. Question number one, how do we get from the square root of 72 to these other four answers? And question number two, is one of these answers more correct than the other? And that's what we're going to learn today, how to rewrite square root of 72 into its most simplified form. We're going to go ahead and do a quick pause again, and we'd like you to go through and define these 10 words in your own words. For example, for rational number, if you just look up rational number on YouTube or Google or something like that, they're going to give you some weird definition of like any number that can be written as a quotient of p over q such that p and q are both integers. Well, that's exciting, and it is correct, but do you know what that means? And if you don't, it really doesn't have any business of being on your paper. So you could do a deep dive and learn what it all means, or you could find a way to explain it in different terms. If you have time, please also provide an example of each of those, and we will be sharing this out amongst the class. So go ahead and pause, take about 10 minutes for 10 of these, and then we will come back together. Ready, set, go. All right, we are back. Let's run through these fairly quickly. Now I'm going to tell you that the definitions I go through are not the fancy schmancy math definitions. Should you understand those? Yeah, probably, but do you have to? No. And I find that students tend to remember things better when it's in their own words than if it's in some weird fancy lingo. So let's begin. Radical. Hopefully when you looked up radical, you realize that it is the symbol that we've used for a square root. This is a radical symbol. And again, some of them will write this without the tail. I always write it with a tail. The radicand is the number that is inside the radical. So in this case, 36 is the radicand. The principal root. Well, to understand the principal root, we should probably talk about a square root first, and then we'll go backwards. Because we already kind of defined a square root, so instead of writing a definition, let's just write two examples. Start with the square root of 4. No, let's go bigger. Let's start with the square root of 9. The square root of 9 is 3, and that's because 3, I'll write it like this, times 3 equals 9. But by that logic, couldn't the square root of 9 equal negative 3? Think about it. If we try that, because a negative 3 times a negative 3, what's a negative times a negative? Oh yeah, it's a positive. And so that does equal the radicand of the original problem. And both of those are actually correct answers. So which one do we write? Do we write both? Just one of them? And it turns out that that's where principal root comes in, because although you could say the square root of 9 equals 3 or negative 3, the principal root is always the positive answer. There's a little bit more to the principal root, but that's about all we need, I think, for today. Great. Now, square root we saw up there found a number that when multiplied by itself, or 2 of the same number, gave us the radicand. But what about a cube root? Well, we could write an example of a cube root here, and in fact, let's compare the two together. Let's look at the square root of 64, and let's look at the cube root of 64. The square root of 64 is 8. Because 8 times 8 equals 64. But the cube root of 64 is 4. And hopefully you figured this out. It's because if you multiply not 2 4's together, but 3 of these 4's together, and you can try this on your calculator. 4 times 4 is 16, times a third 4 is 64. Cube roots look for 3 of the same number that multiply to equal the radicand. Now, going backwards a bit, you might notice this little 3 over here. This is known as an index. It tells us what type of root that is. And you might be saying, well, wait, why does the square root not have an index? Is there one hiding? And there is. In the past, we've only seen numbers like 0 and 1 hiding that are not written. The square root takes it to a whole new level. But it's not going to be a surprise if the cube root of this 3 meant you were looking for 3 of the same number, then it won't surprise you that a square root has an invisible 2, because you are looking for 2 of the same number. And so when we get to an nth root, sometimes you'll see an nth root written like this. It looks for, so we'll say looks for n, where n is a number, n of the same number multiplied together. That's a little vague though, so let's pick a number for n. In particular, let's try 5. Let's try the 5th root, and let's do the 5th root of 32. We may not know how to do that yet on a calculator, but I bet if I gave you the answer, you could at least check it for me. I'm going to tell you the answer is 2. Go ahead, check that, take about 15 seconds. You can check it with the calculator, you can check it by hand, and then come back with me. Ready, set, go. Well, hopefully you checked this by taking 2 and multiplying it 5 different times here, right? Because of the index of 5 over here. 2 times 2 is 4. 4 times 2 is 8. Times another 2 is 16. Times another 2 is 32. Great. The radicand equaled what 5 of the same number equaled. Alrighty, let's continue on. Perfect squares and perfect cubes. Perfect squares are what we saw at the very beginning of class today. We saw 36, or rather the square root of 36 was 6. The square root of 25 is 5. The square root of 64 is 8. The square root of 81 is 9. Those radicands, 81, 64, 25, 36, are all perfect squares. What's an example of something that's not a perfect square? 72. And so you might start to notice the difference in answers. Our perfect squares are all these nice whole numbers as an answer, whereas not perfect squares do not give nice whole numbers as an answer. So let's do a couple examples. Okay, I'm going to list perfect squares out here, and I'll list a few of them. We saw them up above. We said 81, 64, 36, and 25. How come? Well, because the square root of 81 is 9, and I'm going to do the rest of these. The more we practice these, the better we get. Square root of 25 is 5. What's something that's not a perfect square? Not, and I'm going to abbreviate perfect as perf, because why not? Not a perfect square, 72. How do we know that? The square root of 72 is approximately, well, then we saw is 8.485, so on and so forth. Easy. So numbers, when you take the square root and you get that nice integer or maybe whole number answer, perfect square. If, however, when you take the square root of a number, it's not a perfect square, then that's fine too, but expect to get some weird decimal. Perfect cubes, same idea. Numbers where when you take the cube root, you get a nice answer are perfect cubes. So let's list a few of these. Let's try 8. Okay. Let's also do 27. And then let's maybe do one more. Let's do the one we did before, 64. Why are those perfect cubes? Because the cube root of 8 is 2. The cube root of 27 is 3. 3 times 3 times 3 is 27. And the cube root of 64 is 4. 4 times 4 times 4 is 64. What's something that's not a perfect cube? Well, tons of numbers. Let's do one that was a perfect square but not a perfect cube. Let's do, I don't know, 36. So if I do the cube root of 36, this is, and I should have said not out front, sorry, then, this was not great at all. Apologies if you already wrote this. Let's do something like this. Let's say not 36, because the cube root of 36 is, well, I don't even know what that is. We should type it into our calculator. And if we look over here at Desmos, we might say, oh no, can we not do that cube root? Well, we can. And the way that we do it is first we make this obnoxious thing go away. But that's apparently not going to happen, so that's fine. We use this nth root right here. And the first thing that pops up is the index. We want it to be a cube root. And then we move over. The cube root of 36 is 3.301. 3.301. You could have rounded and said 3.302. Awesome. We're getting the idea here. Perfect numbers are ones when you can square root or cube root them, so on and so forth, and they come out to be a nice number. Not perfect numbers are when you take a square root, cube root, whatever, and you don't get a nice integer answer. And that actually brings us down to our last two definitions. Phew, finally, sorry for all the writing. Rational and irrational number. Now, in fact, before I even give you the definition here, we should probably look at some examples. So, examples of rational numbers. Well, some people think of them as only like nice numbers, but there are a lot of nice numbers that are rational, or not nice numbers that are also rational. Like, for example, the decimal 0.3333 repeating, right? It means the 3 goes on forever, though we would never write all those 3s. That would take a lifetime and more. That's a rational number. And the reason it's a rational number is because I can rewrite this as a nice fraction. What nice fraction? 1/3. That's a fraction you should just know. 1/3 is the fraction for 0.33333, 3 going forever. It's an infinite decimal. However, there are many other rational numbers. In fact, almost every number you know is a rational number right now. Even a number like 2. 2 is rational, because I think I can write 2 as the fraction 2/1. In fact, you'd probably have a harder time coming up with numbers that aren't rational. But seeing these examples and hearing me talk about fractions, if you haven't written a definition for this because the one you found was too confusing, go ahead and pause this and see if you can write a definition for what a rational number is. Make sure you include fraction in there somewhere. Ready, set, go. All right, hopefully you're back and you've written your definition. I'm going to give a sample one. Again, this is not a professional mathematical definition. It's going to be something like any number you can write as a, and I'm going to do some quotes, nice fraction. 0.33333 we wrote as a nice fraction. 2 we wrote as a nice fraction. Well, of course, knowing that definition, then I bet irrational number is going to be way easier. In fact, before I give you some examples for irrational numbers, please go ahead and write a definition for an irrational number, knowing that it's very closely related to a rational number. Write that definition, and then unpause me, and we'll see how you did. Ready, set, define. All right, hopefully you wrote a definition that's very, very similar to the other one, something like a number that cannot be written as a nice fraction. Right? It's just like the opposite of a rational number. Now, what are some examples of this? Well, you've actually seen a couple of these today. One of these examples is actually right above us, the cube root of 36, which is the decimal 3.301 and then stuff. Another example is the square root of 72, which was 8.485, blah, blah, blah. And the last example is one that you actually learned around 6th grade when you first started learning geometry, in particular geometry using circles. There's a very special ratio. We use a Greek letter to represent this. Do you remember it? Hopefully you're all jumping up and down saying pi, and hopefully your parents go and make you some pie. But you're right. The other irrational number that you probably know is pi, 3.141, so on and so forth. Now, what do these have in common? Well, they are all decimals, but 0.33333 is a decimal. Really what they have in common is they are all decimals that don't have a pattern in the numbers past the decimal, right? 0.33333 has a pattern. It's all threes. 1/7, if you turn it into a decimal, has a pattern eventually. But if the decimals never have a pattern, and these three decimals here will never start to repeat themselves over and over and over again, then we won't be able to write them as a, quote, nice fraction, and that's what makes them irrational. In fact, every square root, every cube root, every nth root is irrational unless they are a perfect number. So let's take a peek at that. During this unit, it is really going to help you to have a list of all of your perfect squares and maybe even some perfect cubes. We're just going to focus on squares today, but I think cubes is a nice bonus for you to have. So what we'd like you to do is to fill out this chart of perfect squares. Now, we've already done several of these. I'm going to start at this top left box, and I'm going to count down 1, 2, 3, 4, 5, 6. I'm going to start in the sixth box, and I'm going to start with 36. 36 is a perfect square. And then next to it, you're going to have to write small here. The reason why this is a perfect square is because the square root of 36 is 6. It's a nice whole number. We even know the one before it. We know 25 is a perfect square because the square root of 25 is 5. And in fact, based on this, you might see two things. First, the pattern for perfect squares can be a little challenging to see. But the pattern for the square roots of perfect squares is very easy. 5, then 6, this next one is 7, and in fact, if you join me in writing out the answer to when you take the square root of each of these perfect squares, you'll be well on your way to completing this chart. In fact, let's even work backwards, 5, 4, and so on and so forth. When I first started teaching algebra, when you guys were barely born, well over a decade ago now, they didn't used to let you use calculators in Algebra 1. And you had to memorize this chart. You were expected to know your perfect squares up to the square root of something to get 16. And so we used to have all these like time tests to make sure you remembered it, but these days they're pretty accepting of you using a calculator. However, you still should develop a process to find perfect squares. So for example, why is 6 the answer to the square root of 36? Well, it's because 6 times itself is 36. 5 times itself is 25. So how do we find the perfect square that corresponds to 7? We do 7 times 7, which is 49. The square root of 49 is 7. Why don't you go ahead, pause this again, try to fill in these perfect squares, and then we'll talk about the perfect cubes and finally get moving on from there. Ready, set, go. Alright, and we're back. You can go ahead and double check your chart with mine. Realistically, the only numbers you need to have in your chart are the ones that I'm highlighting in purple, just the first number in each box, because the rest is just explaining why they're a perfect square. These 16 numbers that I just highlighted in purple are going to be very useful over the rest of really your math careers, but especially this year and definitely in geometry. Geometry has a lot of simplifying square roots as well. So do you need to memorize these? Not necessarily. Should you? Sure. I would probably make 16 flashcards and put them on there. You might also notice that I ended with a bonus that 256, the square root of 256 is 16. It turns out that the 8th root of 256 is 2. If you multiply 2 times itself 8 times, you actually get the radicand of 256. Alright, I did say the cubes as well. This is again more of a bonus, but it's probably good practice for you. If there are going to be 10 cubes, then we're going to end with these values here. Okay, and as always, if you wanted to find what one of them is, you would have to take this number and multiply it by itself 3 times. So for example, 8 times 8 is 64 times another 8. Oof, 8 times 64, I think that's going to give you 512. Why is it 512? Well, it's 512 because the cube root of 512 equals 8. 8 times 8 times 8 is that. Okay? So if you want to take a quick second and fill this in, you can. If not, you can just listen. I'm going to give you all the perfect cubes. Then we won't do too much else with them this year, but it's just kind of nice to know. So see what you'd like to do, and then once you've made your decision, you can go from there. Ready, set, go. All right, here are the rest. 1,000. 729 is 9 times 9 times 9. This one is 343. For some reason, whenever it's 343 on a clock, I always go, oh, that's 7 cubed. That's the cube root of, cube root of 343 is 7. But maybe that's a math teacher thing. Or maybe it's just me. I don't know. 216, 1, 8, 27, 64, and 125. So these guys are all the perfect cubes. If you do a cube root of any of them, they come out to be beautiful numbers, which is actually pretty crazy, because what this also tells you is if you do the cube root of any number that's not these 10, it comes out to be a gross decimal. There's only 10 perfect cubes from 1 to 1,000. All right, next page, finally. Okay, so here we go. Properties of radicals, or roots. So I'm going to use these pretty interchangeably. Radical is the symbol, root, square root, cube root, so on and so forth. We really use them to mean the same thing. They're not quite the same, but close enough. We're actually only going to cover square roots this year. We used to do cube roots as well, but we're trying to make it a little easier. There are cube roots, 4th roots. I showed you 8th roots before, but we're going to start with some calculator knowledge. Most of your calculators have at least 2 radical buttons. We already discussed how to use this first one. This is the square root right here. Okay. We don't normally write an index, and I'm going to draw a little arrow to show where the index is, for a square root, but if we did, that index is 2. And that's because a square root looks for 2 of the same number multiplied together to equal the inside. The second button on most calculators has a radical symbol that looks like this. Desmos doesn't have this one, but all of your built-in phone calculators do. And they don't all do the same thing. So let's take a look. By hand, we should know the square root of 25. The square root of 25 is 5 because 5 times 5 equals 25. Now, let's go ahead and use your calculator button. So we're going to go ahead and find the square root of 25 on your calculator. And I'm just going to show you on the iPhone over here. I have it back up at the top. And I realize it's not actually an iPhone, but it's the picture, so it's close enough. So if I wanted to do the square root of 25 on my calculator, we'd have to type in 25 first, so it reads 25 up top. And then you'd press the second root of x, or the square root of x, and that would give you an answer of 5. So you do the number first, then the square root. On Desmos, you do the opposite. Desmos, you do the square root first, then 25, and you'll have your answer there. Easy. So we should all get 25. If you don't, something weird is going on, probably with you, probably not your calculator. However, on your calculator, if you try the x root of 25, you're either going to get an error or the wrong answer. And that's because the x root needs you to do something else, right? Your calculator, if you do the x root, is going to take your previous answer and it's going to put the previous answer as the index. So if your previous answer was 5, it's going to put 5 as the index up there, and that's not what you want to happen. What you do want to happen is on your calculator, you're going to want to type in 2 and then the x root and then 25. And what that's going to do is it's going to move the 2 into the x and it's going to find the square root of 25. And I'll let you write that out down here. Okay. Same thing over here. If you try the 5th root of negative 32, you do 5 and then you do the x root and then you do 32, negative 32, sorry, and that should give you negative 2. All right, moving on to the end of this page. See, we're already going faster. Now, many radicals, in fact, you could argue that most radicals or roots give irrational answers, which means our answers can't be written as a nice fraction. For example, if we look at these 10 down below, out of these 10, only 3 are rational numbers. How do we know which ones are rational? We look for those perfect squares. How do we know which ones are perfect squares? Well, you have a chart on the previous page, I think, so we could look to see which of these purple numbers pop up. Or you could start getting good at those squares, and you could look over here and you could say, oh, okay, well, square root of 1 and square root of 4, I know the square root of 1 is 1. This one is going to, of course, be rational because 1 is a perfect square. Okay, so you could say that this is rational if you'd like. Square root of 4 we also know is 2. What's the only other perfect square on here that has a square root, or what's the only other rational answer? Well, hopefully you realize it's 9. 9 is 3 because 3 times 3 is 9. All of the other problems on here, and I'm just going to make a little key so that I don't have to do them all. I'm going to do it in purple. All of the other problems or answers on here are going to be decimals, and they're all going to be irrational. For example, if you put square root of 2 in your calculator, you'd get 1.414, so on and so forth. Okay, this one is also irrational. All of these give weird gross decimals that you can't write as a nice fraction, including this guy. So it should be noted then that in math, if you can avoid writing an infinite decimal, this decimal that goes forever like the square root of 2, then you should. We've seen this before with fractions too. If you get an answer and the answer says 0.66666 repeating, your teacher should have told you, and if they haven't, I'm telling you now, that we don't want you to write this. We don't want you to write and round to 0.667. We want you to write the exact value. And the exact value is normally written as a fraction for a decimal like this. So we would much prefer you write 2/3 instead of either of these. Why? Well, these require an infinite number of numbers to be perfectly correct. But this is the exact answer and doesn't require you to round. Square roots are very, very similar. If you solve a problem and you find, oh, x equals the square root of 2, we don't want you to put that into your calculator and get 1.4142, blah, 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 blah. We don't want you to write that as an answer. We want you to stop here. Should you know how to get a decimal? Sure, use your calculator. But we want the exact answer. We want you to round as little as possible. However, this does bring us to a bit of an issue. And we see, and this is our third page, we see that same issue with fractions. For example, let's say we have a couple students. Let's say we have Abigail and she's solving a problem and she ends up with the answer of 2/4. And then we have Brian and he's solving a problem and he gets an answer of 3/6. And then we have Carlos and he solves a problem and gets an answer of 1/2. Let's say it's all the same problem, and then a teacher goes to grade it and looks at Abigail's work and then Brian's and then Carlos's, and at first glance he's like, well, they all got different answers. But hopefully you're looking at those fractions realizing one thing. All of these fractions are the same decimal. They are all 0.5. They are all the same answer, and all 3 students are correct. As a teacher, I would give all 3 students full credit. However, you also probably learned around 4th grade or so that you're supposed to do something with any fraction. You're supposed to take a fraction like 2/4 or like 3/6, and you're supposed to do what with it? Oh yeah, you're supposed to simplify or reduce it to the most simplified fraction. And with square roots, we want to do the same thing. Now, I said here that we want to make it easy to check everyone's answers, and that's true. There was another historical reason that they wanted people to reduce square roots, and that has to do with our rounding. It was easier to use smaller square roots to do math than bigger square roots, and so someone came up with a way to reduce square roots or to simplify roots. And the way we do it is we're going to factor out all of the perfect squares from inside the square root. And what that's going to do is it's going to make the number inside the square root as small as possible. In fact, we saw that all the way back up on the opener. Look at all these here. We said that they're all the same. Which one has the smallest square root? This is or radicand inside the square root. 72, 18, 8, 12, and 6, and 2. Oh, 2 is the smallest. So we would say that this is the most reduced form. Even though every answer here has the same decimal, every answer is correct. B is what we've been looking for. And so that's what we're going to finish off class with today, how to fully simplify a square root. Now, there are two methods for simplifying square roots, or really any root. I'm going to show you the method that I think is faster first, but this method can also be a little bit trickier, especially if division isn't your favorite and you're not super comfortable with those perfect squares that we saw earlier. But it is a great method, and it ties everything together that we've done so far. And personally, this is how I simplify square roots. But then we're going to give you a second method after that I find a lot of students really enjoy and is maybe a little bit slower but works every time. So you'll notice on this page we have two of the same square root. The square root of 72, the one we've been talking about all class long. And then we have 128, and on our last page 24, and then we have 2 to go from there, where these last 2 you're going to get to pick your method. But the ones where the square roots are all the same, we're going to practice both methods, because you can't just do something one time and say, oh, I don't like that, I'm doing it the other way. You've got to try a couple times through, and then you can start to make your decision. So what does method 1 involve? Well, the first step is you're going to identify any perfect squares that are factors of the number inside, or that radicand. And we're going to use our chart from page 1, so I'll be skipping back to that shortly. Okay, and the reason we're going to identify perfect squares is because we're going to try and rewrite this number 72, which is not a perfect square. This is irrational. We're going to try to rewrite this as multiplying a bunch of perfect squares together that we know the square roots of. Now, how do we know when the square root of 72 is fully simplified? Well, that's when there are no more perfect squares that we can divide out. So what does this look like? Well, the first thing I'd ask you to do is to flip back to your chart and figure out what can we divide 72 by. So we're going to divide 72 by a perfect, and I'm going to abbreviate perfect because otherwise I'll run out of room, by a perfect square. So let's go ahead and jump back to that chart on the first page, and you can just look at my screen here, right? And our perfect squares are, of course, the ones in purple up here. And we're going to see what numbers divide, and sorry, you can probably hear some squeaking in the background. My dog has decided it's a fun time to play, which of course it is. But we're going to go ahead and look at this and decide which of these numbers divide into 72. Now, we should probably remember that numbers that divide into another number have to be smaller than or equal to that number. So 81 doesn't divide into 72 because 81 is bigger than 72. So that means that none of these do, nor do any of these. 64 doesn't go into 72. That's way too big. 49 also doesn't go into 72. So that leaves you with just 6 numbers. And you can start working through those. Like maybe you think, oh, just 25 go into 72. And actually, I'm hoping that many of you are saying 25 doesn't go into 72 because 72 doesn't end in a 5 or a 0. But either way, if we wanted to try that, we would just do something like 72, right, divided by 25. And our answer is 2.88. As soon as you see that decimal, that tells you there's a remainder. So we know that 25 does not go into 72. So I'll leave you to try these other couple numbers, and then we'll discuss your results. Ready, set, go. Well, hopefully you discovered that 36 and 16 and 9 and 4 and 1 all go into 72. Right? That's a bunch of numbers there, isn't it? And actually, I guess 16 doesn't go in there, does it? Awkward. So there we go. There are these 4. Now, if you divide 72 by 1, I think 72 divided by 1 is just 72. That doesn't make the number smaller. And so although 1 is going to go into every one of our numbers, we tend to not divide by 1. So now we're down to 4 numbers, 4, 9, and 36. And in fact, out of these three, I bet most of you are most familiar with the fact that 9 goes into 72. So let's start with that. You could use any of these. It doesn't matter one way or another. But I'm going to go ahead and divide by the perfect square, 9. Because we know the square root of 9, right? The square root of 9 is 3. 3 times 3 is 9. So we're going to take this 72 and rewrite it. Instead of 72, it's still going to be 72, just presented in a different way as 9 times something. 9 times what? Oh, 9 times 8, I think, is still 72. So we haven't changed the radicand, the number that's inside. We've just written it in a different way. Why have we done that? Because one property of square roots, and we're going to further explore this property next class, is that if you have two values or more than two values multiplying, you're allowed to take the square root of every individual value or every individual number in there. And that's useful because we know the square root of 9. The square root of 9 is 3. And so what have we done here? We've reduced the square root of 72 to 3 square roots of 8. How do we know if we've done that right? Well, we already know the decimal equivalent of the square root of 72 is that 8.485. Let's see what happens if we do 3 square roots of 8. That's the exact same decimal, so we know that we haven't changed the value of the number, we've just changed the way it looks, and so that is a correct reduced form. But is this fully reduced? No. And the reason not is because we can still take the number inside the square root and continue to divide that. There's another perfect square in here. So we're going to divide by another perfect square. We're going to divide 8. Maybe I should have put that there. Divide 8 by another perfect square. And so we're going to jump back to our list, see how useful this list is that we made earlier. And we're going to think, okay, what numbers on this list are smaller than 8? Well, there's only 2 numbers smaller than 8. We already said we're not going to use 1, so I think 4 is probably the next number, which we're going to divide by. So doing that down here, we're going to say we're going to divide by 4. And that gives us 3. That's not changing. But the square root of 8, we're going to rewrite using a perfect square, 4 times 2. 4 times 2 is still 8. And maybe skipping that step from before where we distributed the square root like up here, we can just say the square root of 4 is 2. And we don't know the square root of 2. Sometimes students will say the square root of 2 is 1, but then I ask, is 1 times 1 equal to 2? And hopefully you say no, 1 times 1 is equal to 1. So the square root of 2 is just the square root of 2. Now there's no perfect square that we can divide into 2 that will reduce the value 2. You can divide by 1, but that just keeps it exactly the same. So let's do a little multiplication on the outside. Notice we've kept the multiplication all the way through. 3 times 2 is 6. And the square root of 2 stays the same. This is the fully reduced form of the square root of 72. And guess what? If I typed in 6 times the square root of 2 into Desmos or into any calculator, we would get that exact same decimal, 8.485, and so on. All right, now you might be saying, whoa, this was pretty tricky. We had to use that chart of perfect squares. We had to know our perfect squares. We had to know division. Is there a better way? And the answer is yes, there is. Or maybe not a better way, but there's a different way. So let's go ahead and look at this one more time, but over here. Square root of 72. Well, what's the other way? Well, what we're going to do is, maybe using the furthest third of your paper, we're going to go ahead and draw a line, and we're going to use this over here to help us break down 72. And now we're not going to look for perfect squares, and this is what makes this method a little bit easier. Instead of looking for perfect squares, we're just going to divide 72 by anything we can find that goes into 72. For example, you might think, oh, into 72, I know that's even, so 2 divides it. 2 times what? Well, on your calculator, you do 72 divided by 2, and that ends up being 36. 2 times 36 is 72. So this means we've broken down 72 and we're going to cross it out. This is known as a factor tree. There's actually an extra word in front that we're going to go through shortly. And this is something you may have encountered in maybe late elementary school, 4th grade, 3rd grade, something like that. It's a way to break down a number to see what numbers multiply back to equal that number. And 2 times 36 is 72. And then we ask ourselves the question, well, can we break down 2 any further? But that's just 1 times 2. There's another 2. There's no reason to break down 2 and still have a 2. But we can break down 36. And for 36, there's any number of ways to do it, right? 12 times 3, 9 times 4, 6 times 6. All of those work. I'll go ahead and do 12 times 3. Doesn't matter. 12 times 3 is 36. We've broken that down. Now, the question you should keep asking yourself is when we just had 2 times 36, that equaled 72. So the question is, well, now I just have 2 times 12 times 3. What does that equal? Well, if you've done this right and you type in 2 times 12 times 3, it should equal 72. Every time we pause in this tree, all the numbers should multiply back to 72. That's the whole point. We're trying to rewrite 72 with smaller numbers. Now, 3 doesn't break down, but 12 certainly does. 12 breaks down into, let's say, 4 times 3. You could have done 6 times 2. It doesn't matter. And then 4 breaks down into 2 times 2. So let's see what we have. We have 2 times 2 times 2 times 3 times 3. If you multiply all those together, what will that equal? That will equal 72. This is actually known, because now we are left with numbers that don't break down any more simply, as a prime factor tree, because the numbers that are left are prime numbers. Prime numbers are ones where you can only break them down into themselves times 1. So now that we've used a prime factor tree to get these 5 numbers, and by the way, any way you break down 72, if you said 8 and 9 first, you would still get these same 5 prime numbers. Now that we've done that, we're going to rewrite 72. We're going to say, okay, square root of 72. This is the same, and I always go biggest to smallest. We're going to use the 3's first, as 3 times 3 times 2 times 2 times 2. Now, why is this useful? Well, there's one really important fact about square roots that we more cover next class, but is useful for this class. And the fact is, square roots, and we actually saw this on the first page, but we never put it into words, square roots are going to undo squares. Right? On the first page, we said, oh, well, we want to look for a perfect square that equals 3. And we said, okay, well, to do that, we just do 3 times itself, and that gets us 9. So the square root of 9 is 3. But another way to think about that is 3 times itself is 3 squared. Right? That is 9. And so instead of doing the square root of 9, what if we did the square root of 3 squared? 3 squared is 9. The square root of 9 is 3. Well, what that's really doing, though, is to go from here to here, we have 2 things that are canceling each other out. The square root and the square are undoing each other, and then the radicand is just written as the answer. And so we say, and this is very, very important for method 2, after you break down the inside using a prime factor tree, we need to realize or know or remember that a square root and square undo each other. Very, very important. And we'll see that next class. You'll get to keep practicing it. Why is that important? Well, I don't see any squares here. But couldn't we take any pair of numbers and rewrite it as squares? For example, 3 times 3, isn't that the same thing as 3 times itself, or 3 squared? 2 times 2 is 2 squared. And then, unfortunately, this 2 at the end doesn't have a partner, so it just stays as 2. Looking at this one step further, we are allowed to distribute these square roots here. So we're just going to look at the square root of every number individually, and then we can simplify. The square root of 3 squared, those cancel and just leave us with a 3 inside. Square root of 2 squared is just 2. Oh, but sadly, this 2 at the end doesn't have a square to cancel out, so it has to keep its square root. And finishing this off just like before, we get 6 square roots of 2. This is a really nice formulaic way to go through and reduce a square root. And some teachers, by the way, and this is an awesome way to remember it, will tell some fun stories about pairs grouping together, and I'll actually show that on the next one. But you can see that there's a pair of 3s, and at the end, there's a single 3 on the outside. Here's a pair of 2s, and there's a single 2 on the outside. Here is a standalone 2. It doesn't have a pair, and so that stayed inside the square root. And that's a really nice shortcut, and I'm going to show you that shortcut again on the next problem. But at this point, since you guys have seen me do this in 2 different ways, we would like you please to pause this video and try the square root of 28 or 128 on your own, and preferably try both methods. If you get stuck on one, do the other, but definitely try both. And you'll know if you've done it right if you take out your calculator, you type in the square root of 128, and we should probably check that out really quickly, the square root of 128. So if you get the decimal 11.313 when you've reduced, you've done everything correctly. So go ahead and pause me, try that, and once you have unpaused, we will go through it together. Ready, set, go. Alrighty, let's take a look and see what we're going to do here. Square root of 128. Well, if we're looking at this, I see that this ends in a 28. I'm remembering my divisibility rules. If the last 2 digits are divisible by 4, the entire number is divisible by 4. So the first thing I'm going to do is I'm going to divide out a 4 because I know 4 is a perfect square. 4 goes into 12 3 times with 0 left over. 4 goes into 8 twice. 4 and 32. Well, I know the square root of 4, so we're doing fine there. I'm going to keep that one hanging out. But can we reduce 32 any further? Wait, 4 also goes into 32, doesn't it? Can't we rewrite 32, and I should do this in a different color, can't we rewrite 32 as 4 times 8? That's still 32. And now we have 2 perfect squares out front. That's exciting. So let's go a little bit further, and there's going to be a lot of 4s here, I guess. And we look at this and say, okay, we have 4, but what about this 8 at the end? I think 8 can be written as 4 times 2. And now I think we can get our answer because we have the square root of 4, the square root of 4, another square root of 4, and then square root of 2. Square root of 4 is 2, 2, 2. We don't know the square root of 2. It's not a nice integer, and so we leave it like that. 2 times 2 is 4, times a third 2 is 8. And so our final answer is 8 square roots of 2. In fact, you could have done this even faster, and here's the faster way to do it, and I'll show you this over off on the side. What if instead of splitting 128 into 4 times 32, you realize that that is actually just 64 times 2. That is 128, and we know that, or from our chart, we know that the square root of 64, or 64 is a perfect square. The square root of 64 times the square root of 2. Look at how quick this is. The square root of 64 is 8. Square root of 2. We're done. So again, depending on which perfect square you take out, the larger the perfect square, the faster the problem's going to go. But any perfect squares will eventually lead you to the same answer. I did promise you a more straightforward way, if maybe a little bit slower. And so here's that more straightforward way. We start with 128. We say, let's break this down. And again, let's maybe say, looking at this, you're like 128. The only thing I know that goes into 128 is 2. Fine. On your calculator, divide this by 2. 2 goes into 12 6 times. 2 goes into 8 4 times. 2 and 64. We broke down 128. 2 doesn't break down. 2 is prime, so now we break down 64. Maybe on 64 you realize that 8 times 8 is 64, and you're like, cool, we can keep breaking this down. 8 breaks down into 2 and 4, of course, right? And this 8 also breaks down into 2 and 4, or 4 and 2, however you want to write it. 4 breaks down into 2 and 2. 4 breaks down into 2 and 2. All right, I think that's as far as we can go. Let's count those 2s. I see 1, 2, 3, 4, 5, 6, 7 2s. You should maybe try multiplying 2 times itself 7 times and make sure it's 128, but it is. So what have we done here? We've rewritten the square root of 128, and I'll show you 2 ways to do this. Actually, let's do the faster way first. I mentioned a story about pairs, so there's a few stories I've heard. One of the stories involves breaking out of jail and one of the partners being shot, and it's kind of morbid, but the one that I usually tell is maybe not as morbid, but it's equally as sad. So if you have a pair, like so, then you have a friend, and friends like to go play outside. We have a pair, so we're going to go play outside, remembering that multiplication. Pair, go and play outside. Uh-oh, this guy's a loner. He doesn't have a friend to hang out with, so he has to hang out in the house by himself, where the house is, of course, the square root. And then if you multiply all these guys together, 2 times 2 times 2, that's 8, and the 2 inside the square root stays, and we're done. The other way that you could have done this is you could have taken all of the 2's, the 7 2's that are there. You said 2 times 2, there's 3, 4, 5, 6, 7, and started reducing them. 2 times 2, 2 squared. Here's another 2 squared, and another one, and then that guy is a loner, I guess. And then remember that a square root cancels a square root cancels a square, cancels a square. Oh, no square to cancel, so it has to stay inside the square root. And so we end up with 8 square roots of 2. Many different ways to do this. You can totally pick your favorite. So we have just a couple more to try, and then we're done for the day. But same thing before. Why don't you guys go ahead and try these 2, and then we will come back together. Ready, set, go. All right, now you might have had more success with these because we have smaller numbers. 24, I'm going to take out a 4 again, right? 4 and 6. Square root of 4 is 2, so we're left with the square root of 6. Looking at 6, I think the only numbers that are going to multiply to make 6 are either 1 and 6, no perfect squares there besides 1, which doesn't help, and 3 and 2, no perfect squares either. In fact, I think we're done here. That's it. All right, well, that was pretty straightforward. Let's try 24. So doing it a second way with our prime factor tree, let's break this down. And maybe instead of 6 times 4, let's say you think it's 12 and 2. Because you're right, it is 12 times 2. 2 doesn't break down. 12 breaks down to 4 and 3. 4 breaks down to 2 and 2. And then we play the pair game. Pair of 2's comes outside. These guys don't have pairs, so they have to stay inside. And so we finish up with a 2 on the outside. 2 times 3 is 6. And we come up with the same answer. 2 problems to go. These ones look very, very similar. One is 500, one's 1,000, double 500, and that actually comes into play. So let's go ahead and try both of these, and you can unpause after each one or try them both and then unpause. And those are our last 2 problems for the day. Ready, set, go. All right, you're back. I see one very important perfect square hiding in 500. And the very important perfect square is 100. I think 100 times 5 is 500. And so we can think of this as 2 separate square roots. The square root of 100 is just 10, no square root. 5 is prime, it doesn't break down, and we're done. Now, if you're still not great with those perfect squares, you could have broken down 500. It takes a little bit longer, but we can show this over here, right? 500, you're like, oh, maybe that's 10 and 50, and you're right. And this is, 10 times 5. I should be crossing these out. This is 5 times 2, 5 times 2. All right, let's start looking for pairs. I see a pair of 5s. They do not need to be right next to each other. A pair of 2s. And then we have this loner 5 on the inside. So the pair of 5s play outside together, right? They combine together. The pair of 2s play outside together. And then the 5 doesn't have a pair, so it stays inside. And so we can finish this off by saying that this is 10 square roots of 5. Now you can do square root of 1,000 any way you'd like, but I think probably the easiest way for me is I would kind of combine both methods, and I'd say 1,000, isn't that related to 500? So I'd take that 1,000 and say that's just the square root of 500 times the square root of 2. We're treating it as 2 separate square roots. It looks like this. We already know how the square root of 500 breaks down. We found that before. The square root of 500 is 10 square roots of 5. And the square root of 2 doesn't break down. That's prime. There's no numbers in there. And hopefully it's not too much of a stretch to realize that if 2 square roots are split apart, then we certainly could put the 2 numbers inside the square root, the 2 radicands together inside one big square root, right? It's the opposite of what I did here where I split it. I'm just putting them back together. And so finishing this up, we end up with 10 square roots of 10. That's probably our quickest way, right? There are many other ways to do it, but I'll let you guys figure it out from there. So thank you for tuning in to reduce our square roots. Next class, this is going to be really important for writing our answers. We're excited to have you back for solving quadratics using square roots.